Hi! In this video, we'll examine a real-life application of drag forces acting on a falling object. We started with Newton's second law, shown here, and made the assumption that the velocity changed over the duration of the object falling. In this particular experiment, we analyzed a falling object, a plush keychain toy, using tracker software, and then analyzed and idealized conditions using VPython, first assuming that there was no drag force, and then adding drag force in. The results indicate that there is a fundamental flaw in the experiment, most likely generated by a tilted axis. The equations shown here demonstrated the principles at play. We started with Newton's second law and then factored in a non-constant velocity to yield a non-zero net force. For the first analysis run with this equation, we assume no drag force and that the only force acting on the object is its weight force due to gravity. For the second analysis, we added drag as a component of the net force, along with weight. Here are some specifics about this particular experiment. The object dropped was a small plush toy weighing about 0.1 pounds, or 0.0454 kilograms. I dropped it from my height, about 1.55 meters, in a hallway in my house. Here's the video of the actual drop, analyzed in Tracker. As you can see, I set the axes with the y direction being vertical and the x direction being horizontal. The axes here are tilted to account for the slight tilt of the camera. The Tracker software measured the change in position of the plush over the time it descended. The way I set the axes, you can see that it moved in a negative y direction. The position versus time graph to the right-hand side of the screen shows that the plush started falling from zero velocity, or from rest, and then experienced a change in velocity until it hit the floor. It fell for about 0.567 seconds. I then analyzed the idealized motion of the plush, both with drag and without drag, using VPython. This data yielded was used to compare the actual motion with the motion that would have been expected given ideal conditions. Here's the VPython data, yielded with only the weight acting as the net force. As you can see from its position versus time plot, it looks similar to the plot generated from the actual motion in Tracker, and that there is only a downward weight force acting, no upward drag force. This was generated by first plugging in the mass of the plush and setting its initial velocity to zero, then its initial position to zero, or to the origin of the coordinate system that I set. Then the net force was set equal to the weight. I then plotted the VPython data with the actual data, shown here. The expected data is represented by the blue line, while the actual data is represented by the red line. From the plot, it appears that the VPython model initially overpredicted the motion of the toy, and then, about halfway through the time interval, underpredicted its motion. The toy does not appear to reach its terminal velocity, that is, when it reaches the greatest velocity possible and its downward forces balance out its upward forces. I concluded this because it doesn't appear to approach a consistent velocity towards the end. I then repeated the same procedure in VPython, only adding drag force into the net force along with weight. This was done by utilizing the equation drag force is equal to negative b times velocity, shown at the start of this presentation. The proportionality constant, b, was found to be 0.031 newtons per second over meters. As you can see here, the drag force, shown as the blue arrow, acts opposing the downward weight, which is shown by the yellow arrow. I then plotted the three sets of data we now have. The actual motion data and both the idealized no drag and drag data generated from VPython. The VPython data showed very minute changes in position for each time interval between the no drag and drag data, hence the essentially overlapping lines. Because of this, I would have to conclude that the drag force was very small, and that the tilt of the camera caused the position points to be off in the actual data, rendering inaccurate results unable to be compared with each other. I can conclude that the plush did not reach terminal velocity, but that it might have if it had been allowed to fall a greater distance. If the plush had been thrown down and not dropped from rest, it would start at a greater initial velocity, and its terminal velocity would then increase, given that its drag force would increase, using both the negative b times velocity equation and the equation that its magnitude of drag equals speed squared. Because of this, it would have taken longer to reach terminal velocity if the toy had been thrown rather than dropped from rest. That concludes my presentation. Thanks!